Hey, chemistry, Mrs. KJ here. We are going over lesson 1.10, absolute zero. Temperature is measured in degrees Celsius and, of course, kelvins. The coldest temperature is absolute zero. The temperature is measured in Kelvin and is directly proportional to the average kinetic energy. So the internal motion of atoms, the more motion, the higher the temperature. Temperature is a measure of kinetic energy. The concept of absolute zero is a result of the study of behavior of gases. The study of gases and steam engines in the 19th century led to the modern ideas of heat and kinetic energy. From these ideas, thermometers and temperature scales were developed. William Thomson, called Lord Kelvin, developed the concept of absolute zero. In this lesson, you will learn about the Kelvin scale, molecular motion, kinetic energy, and absolute zero. So we have our objectives. We're going to convert a temperature in Celsius to the Kelvin scale, which you've already been doing. Interpret graphical information about temperature in Celsius and kelvins. Describe 0 Kelvin as absolute zero. Describe the relationship between average kinetic energy and temperature. Show that Kelvin temperature is directly proportional to the average kinetic energy of the particles of a substance. So directly proportional. That means when the energy goes up, what happens to Kelvin? It goes up as well. Keywords, make sure you hit pause and write these all down. Absolute zero equals a temperature of 0 Kelvin at which all atomic motion ceases. This is the only time atoms do not move, and scientists have never actually gotten this cold. They've gotten really close, like 0.001 Kelvin, and things move really slow. Even light moves slow. Like if I would turn on a flashlight over on this side of the screen, usually it's just instant, right? That the light would be shown all the way across. But when you get so cold, you can actually see the beam of light traveling. So super weird stuff happens, and Einstein even said time might stop if we get to 0 degrees Kelvin. So super cool stuff. Kelvin is a unit on the Kelvin scale and a measure of temperature, and kinetic energy is the energy associated with the movement of any mass. So anytime we're talking about movement, we're talking about kinetic energy, and specifically with temperature, we're talking about the internal motion of the atoms. And if you would like to go into the lesson and print off the study guide, feel free to do that. So explore absolute zero. As you read through the lessons, make sure you take notes. Motions of gas molecules account for the properties of gases. In an ideal gas, the particles are in constant random motion. The particles collide with one another and the walls of the container. The motion of these particles account for the properties of gases. So hopefully so far this has been a review. If not, make sure you write this stuff down again. Pressure, the combined forces of the collisions between the particles and the walls of the container. The more motion, the more collisions, and the greater the pressure. Volume, the moving molecules create space. The more motion, the farther the distance between molecules, and the greater the volume. Temperature, the measure of molecular motion. So let's take a look at this. All right, so we have our container at 200 degrees Celsius. The tip of the thermometer. So we measure temperature based on how frequently the molecules are hitting the thermometer, and that causes energy to go from the molecules to the thermometer, which causes the alcohol or mercury inside to rise. So if we have, it was 20.0 degrees Celsius. So you can see that we have different collisions happening, and it's the overall average of those collisions that gives us the temperature. Things in motion have kinetic energy. Kinetic energy, or KE, is the energy of any mass that has velocity. Velocity means speed in a certain direction. So kinetic energy is the energy of any mass that has velocity from an atom to a planet. Gas molecules move, of course, so each has its own kinetic energy. So each one of these has energy. When you heat a gas, the kinetic energy of molecules goes up because each molecule moves faster. Each molecule has a greater velocity, so speed in the direction. When you cool a gas, the kinetic energy It's not letting me cool it. The kinetic energy of each molecule goes down because each molecule has lower velocity. All right, so if I were able to move this to medium, they would move slower, which means the temperature would be lower. Temperature is the measure of the average kinetic energy of the molecules in a system. If you measure the kinetic energy of a group of runners and divide by the number of you measured, so divide by the number of runners, you will come up with the average kinetic energy for the runners. With systems of atoms and molecules, you can do much of the same thing. You find the average kinetic energy of the particles in the system. The average kinetic energy of a system is called by a specific name, temperature. Temperature, no matter what scale you use, Fahrenheit, Celsius, or Kelvin, is a measure of the average kinetic energy of the particles in the system. So make sure you write that down if you haven't already. And so the more average kinetic motion, the temperature. Well, all right, so let's move to particle view. And there you go. As we increase the temperature, we are not only increasing the pressure, but the reason the temperature and the pressure are both increasing is because we are having faster motion, a higher average kinetic energy. The more motion, the more collisions, the more pressure. The more motion, the higher the average motion is, and that is our temperature. So right now they should have been moving really crazy fast, which, yeah, they don't always, but oh well. So they move really crazy fast. They have the most collisions, therefore the highest pressure, and the overall speed is the highest, which means the overall temperature is the highest. Lord Kelvin introduced absolute zero. Making use of theories of kinetic energy and molecular motion, British physicist William Thomson, or Lord Kelvin, introduced the concept of absolute zero. Temperature is a measure of the average kinetic energy of molecules in a gas. When average kinetic energy increases, we say the temperature goes up. When average kinetic energy decreases, we see the temperature goes down. Using a thermometer of any scale, we can state how much it goes up or down. Kelvin reasoned that there must be a temperature at which the average kinetic energy is zero and all motion stops. Because think about it, if we go hotter and hotter and hotter, they move faster and faster. If we get colder and colder, they move slower and slower. There's got to be a point that they stop moving, according to his ideas. He called this temperature absolute zero. Nothing can be colder than absolute zero because temperature is a measure of motion, and all motion, atomic, molecular, ceases at absolute zero. Absolute zero is one of the reference points used in the absolute temperature scale. All right, so Daniel Gabriel invented Fahrenheit. Andreas Celsius has the temperature scale, and what he did is he just said, okay, I have frozen water, that's zero. I'm boiling it, that's 100. Let's just divide that into 100 even increments. So that's how he came up with that. I honestly have no idea about Fahrenheit. If it's interesting to you, look it up, and if you think it's interesting, send me an email and let me know why. Lord Kelvin develops his absolute scale based on absolute zero. So he's saying absolute zero is where motion should stop, and then he got 272 water freezes, 373 water boils. And your temperature is 309. That's right, you can go to your mom and be like, Mom, I don't feel good. I'm pretty sure my temperature is 309. The Kelvin scale is used for measuring temperature. The Kelvin scale of temperature started with two reference points. Initially, the reference points were absolute zero and the freezing of water, 273.15 Kelvin. At that time, the absolute temperature was defined as kelvins, not degrees Kelvin. Notice that the word Kelvin is spelled with a small k. However, the symbol for Kelvin is a capital K. When you read absolute temperature in a book or problem, it means temperature measured on the Kelvin scale. And again, they don't say degrees Kelvin. Use these formulas to convert temperature between Celsius and Kelvin. In the laboratory, temperatures are often measured in degrees Celsius and converted to Kelvin. The formula conversion is Kelvin equals degrees Celsius plus 273.15, but it's usually rounded to 273, and we'll use 273. So degrees Celsius, if you have Kelvin, it's Kelvin minus 273 to get your degrees Celsius. For example, if you have 300 Kelvin, you have to minus 273 to get 27 degrees Celsius. All right. So you have a sample of gas at 25 degrees Celsius. What's the temperature in Kelvin? Add 273, it's 298. Conversion 2, if you have 500 degrees Celsius, it's how much? 773 Kelvin. I'm going kind of fast through these because I know we've been doing these already. So negative 40 degrees Celsius is positive 233 Kelvin. Again, the reason we use Kelvin when we do all the gas laws is because it's always a positive number. How cold is absolute zero? You are probably most familiar with temperatures such as the freezing point of water or the boiling point of water. The average surface temperature of the Earth is 15 degrees Celsius or 288 Kelvin. These temperatures are well above absolute zero. Most gases condense to liquid at a low temperature. For example, liquid hydrogen and liquid oxygen, which are fuels for the space shuttle, boil at 20 degrees Kelvin and 90 degrees Kelvin respectively. Okay, so right now in your home, you're at like 288 degrees Kelvin. I know you're not supposed to say degrees, but it kind of helps think about it. So you're at 288 degrees Kelvin. If you wanted to make the air into liquid, which we can do if we get cold enough, you'd have to be at 90 degrees Kelvin. That's a huge difference. If you wanted to get liquid hydrogen, you'd have to be at 20 degrees Kelvin. Now, the ideal gas law mathematically relates pressure, volume, temperature, and the amount or moles. Gases behave differently near absolute zero. They may condense into liquids like this, or even solids. Yeah, you can have a brick of oxygen. How weird is that? Or they may demonstrate other properties such as superconductivity. And just because people usually end up asking, outer space is 3 degrees Kelvin or 3 Kelvin. Why do scientists try to reach absolute zero? Okay, because really it could be kind of dangerous if time actually stopped, right? Well, there's a reason they want to get things super cold. Very interesting things happen to matter at low temperatures. For example, when certain materials are cooled to near absolute zero, their electrical resistance almost disappears. These materials, such as metals, alloys, and other compounds, are called superconductors, and they can be used to make powerful electromagnets that produce little or no heat and consume little electricity. Okay, think about when you plug in your computer and you touch your power cord, the box part, it gets really hot, right? Well, that heat is because of the resistance in the wires and everything else. And that's wasted energy. That's wasted money. Yeah, when you have heat coming out of your appliances, that's wasted money. So, of course, they want to figure out things with little or no heat to consume little or no electricity to save money. Such magnets can be used in particle accelerators that are used to smash atoms and explore the structure of subatomic particles like the proton and neutron in quarks, or the energies that hold the nucleus together. To get to near absolute zero, scientists use a cascade cooling process that repeats, pressurizing, evaporating, and cooling various gases in sequence. Scientists have come within a billionth of a degree Kelvin of absolute zero. So how low can you go? And superconducting magnets cause levitation, so they float basically. And that's used for the really high speed trains. Like in Germany, they use them a lot. In Japan's probably where you heard of them, where they go like 300 miles an hour. We'll come back to the process. Absolute zero is the measure of the average kinetic energy of motionless molecules. Molecular motion accounts for the properties of gases. Molecules move and thus have kinetic energy. Heating or cooling gases adds or removes energy and changes a molecule's kinetic energy. Temperature is a measure of the average kinetic energy of all molecules. All molecular motion stops at absolute zero or 0 Kelvin, and nothing can be colder. Absolute temperature is measured in Kelvin. The physical properties of substances at low temperatures have interesting applications because they change properties. Temperature is measured in degrees Celsius and Kelvin. The coldest temperature is absolute zero. Kelvin is directly proportional to the average kinetic energy. The more the molecules move, the higher the temperature. Temperature is a measure of kinetic energy. If you want to look at reaching ultra low temperatures and the whole process, it's pretty cool, but it's something that you can do because it's an exploration, and here's the link.